Hello everyone, I'm Pekon Gupta and I'm here with my colleague Arthur Sanyo from Smart Modular to discuss about computational memory, the concept of moving compute near the data. So let's discuss with an example over here. What you see over in this slide is a standard data flow or a logical view of how an end customer who is using a map software on his mobile is trying to locate a coffee shop nearby. The data flows from the application, which is on the mobile, through a series of network or telecommunication infrastructure into a data center where it gets analyzed in different steps. There is a storage system where you get fetch the data for running through the analytics. There is a database, there is security mechanisms, and all that data, when it is processed, is returned back with a response back to the user, and it's displayed on the mobile. All this happens in a fraction of seconds, or probably within few couple of seconds. And there are thousands of such queries generated per second. So the end result is the network gets hundreds of GBs of, or has to route hundreds of GBs of data per second without any packet drops. Storage engines get thousands of requests in every second, and even the fastest CPU running a software alone cannot match that line rates. Therefore, there is a need of dedicated hardware which can pre-process the data and assist the CPU in processing some of these queries which are very time dependent. This is where hardware accelerators come into play. There are three types of hardware accelerators which we are considering for today's discussion. The first one is network accelerators, or the network interface cards. These are smart NICs or network interface cards with built-in packet processors. These packet processors can decode the packet headers of network protocols at the line rate speeds. This type of accelerators allow pre-filtering and rerouting of the network traffic at hundreds of gigabits in either direction. There are many players in this, and I've just listed a few of them. The other type of accelerators are storage accelerators. We also call them computational storage devices. These are predominantly SSDs with built-in programmable compute engines like an FPGA or a processor along with an NVMe controller. But from a host standpoint, these are block devices which can do inline compression, encryption during a standard read-write operation to a NAND device. But our today's focus is memory accelerators. We also call them computational memory devices. Computational memory devices are very much similar to computational storage devices, but they operate at byte level or cache level granularities. And this is the key difference between the computational storage device and a memory device. Thus, a data in a computational memory device is directly addressable and accessible at much lower latency than a standard block device. This also enables a simplified software architecture because you can reuse the existing API framework through which the users access the system memory. And overall, this improves the performance of the system. Now, let's look at some of the computational memory devices available in different types of form factors. We have three types of form factors shown in this slide. And let's start with the one in the left, which is in a DIMM type of form factor. The biggest advantage of having a computational memory device in a DIMM form factor is it gets the lowest latency and has the best performance because the memory is directly connected to a processor bus through a parallel interface like DDR4 or DDR5. However, that also brings another set of challenges, as the maximum speed of a memory channel is determined by slowest running DIMM on that channel. And if your computational memory device is the slowest running DIMM, then it brings down the speed of the entire bus, thereby degrading the performance of the entire system instead of boosting it. There are other mechanical and thermal challenges which limit the amount of offload you can do on a computational memory device in the DIMM form factor. Since these DIMMs are very closely spaced and the PCB real estate is very tight, adding any large or tall compute engine or processor component is not an option. The thermals are another challenge because some of these DIMM form factors cannot go beyond 15 to 18 watts of total power. And therefore, there is a trend to move towards EDSFF form factors like E1.S or E3.S. These form factors solve some of the challenges which we've seen over here. However, they add extra latency because of converting a load store access into a serial bus and then deserializing it back in the memory controller. But a part of this latency can be absorbed by offloading simple compute functions like searching, sorting, or just doing a memory initialization in the computational storage device. An E3.S 2T form factor can sustain up to 40 watts. This gives end user a substantial headroom to run heavy algorithms in the memory device itself. Now let's look on the last type of form factor, which is PCIe Gen, which is card electromechanical form factor. These devices go one step beyond EDSFF and allow customers to scale from hundreds of GB to terabytes of memory. However, they have an additional benefit that they allow users to mix and match memory DIMMs of different capacities and source from different vendors. Some of the memory DIMMs can also be reused from your existing existing servers, which had to be thrown away when you upgraded the system. So this extends the lifetime of your overall memory investment, which was not planned for new devices. In the next few slides, we will focus on computational memory devices, specifically focusing on PCIe Gen form factor. I'll let my colleague Arthur Sanyo discuss more about this.
Thank you, Pekon. So what we're showing here is an example of a computational memory device called Kestral in a PCIe Gen form factor. It runs on PCIe Gen 4 and uses standard Intel Optane DIMMs as well as DDR4 standard RDIMMs. There are 4 DDR4 slots on this card, each of which can be populated with 5 12 gigabyte Optane DIMMs, making up a total of 2 terabytes. At the heart of this device is an Intel Stratix 10 FPGA, which converts the PCIe Gen 4x16 interface into Intel's DDR-T interface. Using an FPGA instead of a hardened ASIC allows users to offload compute functions on this card. The FPGA also has built-in quad-core ARM A53, which can be used for running firmware and multi-threaded algorithms on the 2 terabytes of data memory on the card. This card utilizes less than 150 watts of power and can be cooled passively. This computational memory device opens up numerous possibilities of moving the compute near the data. Next slide, please. So moving the controller logic outside the processor to the memory module has multiple benefits. First of all, as Pekon mentioned, it decouples the CPU architecture from the memory media. This makes architecture CPU agnostic. For example, a PCIe add-in card, which we showed earlier, uses Intel Optane DIMMs, can be connected to any CPU platform via the PCIe bus. This architecture gives freedom to system integrators to upgrade memory technology independent of this CPU architecture. Another key benefit of moving compute near the data is reducing the copy and discard. A few algorithms like content addressable search or table lookup or map reduce operations require fetching data from memory and using it only once and discarding it. This wasteful copy can be avoided by moving those functions to the memory module. Offloading such data-intensive operations to the computational memory device will not only free up the CPU, but also improve the efficiency by reducing cache trashing. And lastly, as we discussed earlier with the form factors, memory modules, the DD4 RDIMMs can be reused on this new Kestral add-in card, thereby reducing overall ROI investments. Pekon, back to you.
Thank you, Arthur. Now let's continue on looking at other use cases of computational memory device. In this slide, we will discuss how a computational memory device can improve the performance of a storage array. When a computational memory device like Kestral is attached to a PCIe switch along with other NVMe SSDs, it can prefetch the data during the reads, thereby minimizing the delay in data reconstruction. During write operation, the write data can be buffered by the same device and then committed slowly to a physical HDD or an SSD. A few devices like Kestral also have built-in DMA engine, which can be used as a data mover function. This allows direct transfer of the data from system memory, which is the DDR4 or DDR5 DIMMs attached to the CPU, to a storage pool, which is sitting on a PCIe bus, thereby minimizing any CPU intervention and offloading or freeing up the CPU from costly interrupts, which are triggered during a data movement operation. In addition to these fixed functions like inline compression, encryption, or key value mapping, some can be added to the data path logic, which improves the overall efficiency of a storage architecture. Therefore, it may be more cost effective to just use one computational memory device in a system instead of using multiple computational storage devices. This architecture brings down the TCO of the entire system use case. Now, let's look at the real numbers from the hardware side. The benefit of computational memory device can be seen by comparing its latency with some of the fastest SSDs available in the market as of early 2022. In this table, we are comparing Kestral, which is the computational memory device running on PCIe Gen 4 by 8 interface, with a similar capacity SSD from different types of vendors. What we see over here is that Kestral is able to match the performance of what the standard SSDs give, but it has considerably lower latency than all other SSD devices or block storage devices available. This makes computational memory device like Kestral a very good fit for applications where turnaround time or SLA is critical for an end application. Some of these applications we have already discussed earlier, but the ability to offload custom functions or accelerate along with the lower latency makes this class of devices, or what we call as computational memory devices, very attractive for some of the key functions we discussed earlier. So summarizing the benefit of computational memory architecture, the biggest one is it decentralizes the compute by moving fixed compute functions near the data, and it reduces the wasteful copies and frees up the CPU cycles, as my colleague Arthur suggested in a previous slide. This also decouples the nuances of memory management and decouples the memory interface from a CPU architecture, allowing end users to upgrade their memory independent of the CPU. And by choosing the right form factor, you can reuse your existing memory modules in a new attachment, getting more returns out of your investment. So I hope this slide will help you decide on which type of computational memory device you would want to deploy in your system. With this, we like to end our presentation. Hope you liked it. Please take a moment to rate this session. Thank you.
Thank you, everyone.